Let us try to solve this system of equations. The first thing you should do when you see this system of equations is you should try to transform it into Gaussian format. Here's what I'm going to do. I'm going to write the coefficients of each variable here. The coefficient of x is 1. In the second equation, the coefficient is 1. Third equation, the coefficient is -3. I do the same thing for the other two ones. This is my coefficient matrix. And then there is my matrix, my vector of variables. So if you know how to apply a matrix to a vector, you would know that if you distribute this, you get the following. You get x1 plus 3x2 minus 5x3. Now this is, on the other hand, equal to my vector of solutions, 4, 7, and -6. Because I want my left-hand side equation to be equal to my right-hand side equation. So this is good. Usually this is called B, usually that is called A. The first step you need to do is to augment B to A. Let me make this extremely precise. So I take the matrix A and I augment to it. I make some extra space for B here. You could think of this line as an equal sign. So what I'm saying right now is x1 plus 3x2 minus 5x3 is equal to 4. This is what the first row is telling us. This is how I should read it off. The third row is telling us minus 3x1 minus 7x2 plus 9x3 is equal to -6. This is also how I should read it off. So this is good. It will be amazing if we can have something that looks like this. X1 is equal to this, x2 is equal to that, x3 is equal to that. The only way we would have this is if the following happens. You have 1x1, 0x2, and 0x3 equal to something. I think you see how this works now. So this needs to be 0, this needs to be 1. My apologies. And all the other variables in the same row should be 0. Now, this would ideally translate to the following system. So if I want to write this as an augmented matrix, then I can say that my publicly stated goal from this Gaussian procedure is to have 1, 0, 0, 0, 1, 0, and 0, 0, 1. That is really the goal of what I'm trying to do now. And this should be equal to something, this is equal to something, that is equal to something. So that is the goal. It is true that this is how we should proceed. So let's let's do just that. Ones at the diagonal and zeros everywhere else. And there is, of course, a simple question one might ask, and that is, how do you reach this goal? Well, this is not too difficult. If you learn what Gaussian elimination is about. So Gaussian elimination is a more compact way to eliminate variables. For example, here I have x1, 3x2 minus 5x3 is equal to something. Here I have also x1, something, something, something. So what I can do is I can add the negative counterpart of this equation to that equation. And when I do this, the x1 goes away because the negative counterpart is going to be minus x1. I add the minus x1 to x1, I get a 0 here. Yes, I get some new stuff for the other components, but step by step, if I keep eliminating components, then I can reach my ultimate goal. We will proceed row by row, column by column. So here I have my 1, I'm happy. I just need to make a 0 here and a 0 there. The way I would make a 0 in the second equation is if I multiply the first equation, so the first row, by minus 1 and add it to the second row. Similarly, if I multiply the first row by 3, I'll get a positive 3 for x1. And then I add it to the second equation. So as you can see here, I multiply this, for example, by 3. And I add it to the third equation. When I do this, it's great because my variable vanishes. Yes, I get some new things here, but my variable vanishes. And I continue on to do this until I reach the solution. And so let's actually do that. I have a thing which you could have in your draft that would help you, follow the steps. Because the problem with Gaussian elimination really is that it takes lots of steps. And it can be very complicated to follow up and to make sure you're on the right track. So let's try to take care of that. This is our row. We're multiplying by minus 1. So this will be minus 1, minus 3, and 5. This will be minus 4. This is my new equation. Now remember, I'm adding this to the other row, which is the second one. So what happens when I add this? 1 minus 1 plus 1 is 0 as designed. Minus 3 plus 4 is 1. And these are the remaining results. So this is my updated equation, you could say. So my updated equation, I copy the matrix that I have here, well, the augmented matrix that I have here. And this is going to change, obviously, into these new values, 0, 1, minus 3. And then this is going to be just 3. I still need to figure out what's going to happen here, the last row. So I proceed exactly in the same way. I have my old row, I'm multiplying it by positive 3. This will give me 3, 9, minus 15. The other row to which I'm adding these new values is the third one. Then I should now add the values. This will give me yet another 0 by design. That's how I chose my factor of 3, so that I can effectively cancel out this one variable. But for the other ones, they do not necessarily have to cancel. 9 minus 7 is 2, minus 15 plus 9 is minus 6, and minus 4 plus minus 6 is minus 10. Great, then I've successfully secured the zeros here. I'm happy with this. And I'm one step closer to my goal. And the next step is to make zeros in the other two diagonals. And there's something really nice will happen now. And that is, I will only focus on this part on the right. I don't need to focus on the part on the left. The mission is done. Because here's the thing. If I want to make a 0 here and a 0 there, then I should multiply this row by minus 3, cancel out this positive 3. I should multiply this row by minus 2 and add it to the second row to cancel out the 2. But then what's so amazing about this now is that there's a 0 here. And if there's a 0 here, then it doesn't matter what I multiply the 0 by. And if it doesn't matter what I multiply the 0 by, it will give me 0. Then it doesn't matter what I will add. So whatever I multiply and add to this one or that one, it doesn't matter. It will always be 0. I'll always be adding 0. You'll see this in a moment. I'll clarify it. So here is our new row, 0, 1, minus 3, and 3. The first factor which we will apply is, let's say, is minus 3. The other row that we're looking to add the value of minus 3 to is 1, 3, and minus 5, and is equal to 4. So we multiply this by 3. 0 times 3 is 0. It doesn't matter. And 0 plus 1 is 0. It's 1. So the value for the other row always stays the same. I don't need to worry about it. I hope that is clear now. 1 times 3 is 3, minus 3 times... this is minus 3. Minus 3 times minus 3 is positive 9. And then this is negative 9. Negative 9 plus 4 is negative 5. This is 4, and this is 0, as designed. So just give myself a little bit more space here. It goes in very nicely. So this is the new set of values for my upper first row, or upper first equation. So it was this, and now it became like that. This became a 0, of course. This will also become a 0 in a moment. Let's do that. So we multiply by minus 2. 1 times minus 2 is minus 2. This is positive 6, and this is negative 6. The other row to which we're adding this is this one. So it's and now when we add this, I think there's a surprise for us here. So yes, this will be 0. This will be untouched. Minus 2 plus 2 is 0. Minus 6 plus 6 is 0, and minus 6 plus minus 10 is minus 16. So let's take a moment to try to grasp what is going on here really. So how can we read off this equation is my question. And the answer is that this equation reads precisely the following. It says that 0 x1 plus 0 x2 plus 0 x3 is equal to minus 16. You see? And this doesn't make sense. This doesn't make sense. The sign means a contradiction. So this is a contradiction. What does this contradiction mean for our problem? Well, many things. I want to make sure that I haven't made a computational mistake. Please give me one moment. Yes, I was able to spot the mistake. And so the mistake happened when in the very beginning, when I multiplied this 4 by 3. This should give me 12. And when I take away 6 from it, I should get a minus 6 and not a minus 10. And if this is a minus 6, and then, well, not even a minus 6, I'm doing it again. It's a positive 6. 12 minus 6 is 6. So this is 6. Then now I get a 0. So this is another case. Where this is 0. Because, minus 6 plus 6 is 0. Now, this is not a contradiction, but it is useless, right? If you think about the set of all vectors which satisfy this equation, it's just every single vector can satisfy this equation. Every single triplet of vectors can satisfy this equation. So it's not a useful equation. It doesn't have any data involved. So what do we do? What we're going to do now is we're going to get rid of this equation. I'm not referring to this. I'm referring to that. I'm just making a nice box on the side. So you have this system. I will write the system without the equation that we've just found to be useless. So in such an instance, you would say that your system is linearly dependent. So one of the equations is a copy of the other, or you can obtain the third equation by adding one of the two equations together. And you could probably play this game. You could try to find which combination gives you the third equation. You could play this game. But at least for here, we know that our system is linearly dependent. This line is just for illustration. This is something we do for our personal understanding of the problem. It doesn't have anything to do with the practicality of the solution. Well, what happens in this case? Now we don't have the diagonal, we just have two equations. We don't have the nice diagonal that we were talking about. Remember, this was our goal, and this was not possible. So we want to have the nice box where you have ones and zeros. How do we obtain this? First off, let's write down these equations. So the first equation is saying that x1 plus 4x3 is equal to minus 5. The second one is saying x2 plus minus 3x3 is equal to 3. And now we only have two equations, so we can only solve for two variables. You could say this is an under constraint system. And now, if I want to find at least the value for two variables, then I would simply do this by sending these to the other side. When I do this, of course, the sign needs to be changed. You need to be careful. So x1 is equal to this and x2 is equal to that. And guess what? I can even do this in the matrix format. So I can move this equal sign around and switch up the signs. And then it is great, because I have my box, but it is a bit smaller. It's a bit of a smaller box, you could say. Okay, then I have a value for x1, I have a value for x2. Do I have a value for x3? Not really. I can't really say anything about x3. x3 can be anything. So I just write x3 is equal to x3. Just any real number. And this system of equations, this very precise system of equations, I can work with and I can write a solution for. So I write x1, x2, x3 is equal to the following. So x1 is equal to minus 5 minus 4x3. x2 is equal to 3 plus 3x3, and x3 is just equal to x3. I hope you don't mind if I write a vector which has all the constants, so minus 5, 3, and 0, because remember this is just x3 plus 0. And then I can write the vector which has the x3s. This has minus 4, this has 3x3, and this just has 1x3. This is completely fine because, if we just apply vector addition, then you get the same thing back. Now, finally, I want you to notice that our x3 is a common factor in all of these terms. So it wouldn't really hurt at all if we take this x3 as a common factor. And then we say that this is the solution to our equation. We say x3 is a real number. Some people like to say, okay, let's set x3 to be, some lambda, and I'll let this be lambda be like this. But this is really just a matter of taste. I personally prefer the x3 one, because I feel like it's more straightforward. You're just saying that x3 can be any number. And with this, you should be able to obtain the solution. You need to be careful because there is lots of room for mistakes. This is nice. It should help you reduce your level of mistakes that you might encounter, but it won't limit it to 0, because even as you can see, I've already made a mistake, and I think I will deliberately leave it here. So I won't edit it or do anything about it, because I really want to emphasize this. Mistakes can happen, and you just need to be very careful when you do this. But if you use, for example, a draft like this one, then it should also be of great help. Finally, I want you to notice, of course, that we have 3 equations and 2 variables. Maybe if I say a couple of words on this, it just means that we have 1 degree of freedom, because we have the freedom to choose one variable to be any value we want. So we know that x1 is this, and x2 is this. But x3 can be anything. What this means is that I can choose x3, for example, to be 0. Then I will obtain two values for x1 and x2. So this is the one degree of freedom I have. I use up my degree of freedom, I immediately obtain a solution. So -5 and 3. I change this to be 1. I get -9 and 6. And so on and so forth. So with one degree of freedom, you have one choice, you could say, for this new variable. And with this one choice, if you make it, you can determine how your system of equation looks like. So yes, it is underdetermined in the sense that there is no specific triplet which gives you the full solution, but at least for the infinite class of solutions that you have, you can constrain it to down to the choice of your parameter, which is x3. And then from there, you can obtain any solution you would like, depending on this one parameter. So this one choice, this one degree of freedom.